Welcome to MathGlider, where we glide mathematics right into your mind. In this video, we're starting a new series on metric spaces, which is an important topic of real analysis. We will be covering the material in detail and referring to two textbooks throughout this series. First one is Topology of Metric Spaces by Kumaresan and Real Mathematical Analysis by Charles Chapman Poe. So this is the course designed to help B.Sc as well as M.Sc students, and it will also be useful for those preparing for exams like CSIR-NET, GATE, JAM, or various Ph.D. entrance exams also, or even UPSC Maths optional. So this series will go topic by topic with clear explanations, proofs, and examples. So if you're studying this subject or just want to understand it better, make sure to follow along. We all have an intuitive idea of what distances mean, like how far one point is from another in space. In school, we have learned this usual distance formula between 2 points in the plane, which is the straight line distance we calculate in usual. But in mathematics, we can generalize this idea much further. So the goal of this topic is to understand what distance really means and what it should follow. Like how can we define distances in more abstract settings rather than saying that distance is just a straight line distance between this, and we can do many other things with it. So this leads to the concept of metric, which is just formal way of defining the distances between elements of any set. So this will not be the distance between R or R2. It will be more general sets than that. Once we define the distance properly using this metric, we can talk about another ideas on this metric space. And any idea we talk about in this metric space, we can apply those on any example of this metric space. So this idea, you see that it is very important to think like that. We generalize something, we do things on that general tool, and then we can this apply this on any example of that general tool. Okay, so let's get started. So we know this Euclidean distance we have learned in high school or in 12th standard, right? So let's take 2 points x1, y1, x2, y2 in a R2 space. So we calculate the Euclidean distance by this formula of square root of x1 minus x2 whole square plus y1 minus y2 whole squared. Okay, let's take this 2 points. This one being x1, y1, and this being x2, y2. Okay. So this Euclidean distance, you know what this distance is, right? This distance is the straight line distance between these 2 points, and it is calculated by this formula, right? This formula gives us the straight line distance. So up till now, you know the distance as in this Euclidean distance, right? So we will see what are the properties satisfied by these distances. So we can generalize the idea of distance much further. So we will think about the properties of this distance. Okay. So first of all, you can see that positivity property. Let's check if this Euclidean distance has positivity property. So any 2 points you take, the distance will be always positive, right? Unless the point and point itself, right? If we are checking the point distance between this point and this point, again it will be 0. But any different 2 points if you take, distance will be positive, right? We are taking the positive square root of something inside this, right? Okay. Second property, let's check symmetry. Let's take 2 points. Let's make this A and let's name this B. So distance between A to B is same as distance between B to A, right? Distance between A to B and B to A are same. So this Euclidean distance satisfies the symmetry property. We say distance between A to B is distance between B and A. So we have this property inside Euclidean distance. So we noted that it satisfied symmetry also. Now let us say triangle inequality property. You know what is the triangle inequality property in usual? Distance between A to B, let's say, this should be smaller than distance between A to C plus distance between A to uh, B to C, right? And we know, like, if we can literally see, let's take three different points, namely A, B, and C. Now take distance between A and, okay, sorry. Now let us take distance between A to B. This distance will be less than distance between A to C plus distance B to C, right? This plus this will be greater than or equal to this distance. So this is the straight line distance. So we can easily see that this Euclidean distance satisfies triangle inequality property. Okay. So that's about Euclidean distance, and it satisfied three properties for us: positivity, symmetry, and triangle inequality. Okay, so now we will think about the distances in a little bit weird manner. Like we have, you must have not seen this very often, but this is a different approach to defining distance. So in Euclidean distance, you know that if you want to find out the two distance between 2 points, you just simply draw the line and its distance, its length is the distance. Okay, so now we are in chessboard distance. So you know, if you are at any point here and if you want to travel some distance, let's say you want to travel distance 1. So in chessboard you can go 1 here, right? 1 here, or 1 here, or 1 here. Like distance between this and this is 1, distance between this and this is defined as 1, this and this is defined as 1, this and this is defined as 2, this and this, let's say, is defined as 1, 2, 3, or 1, 2, like 1, 2, 3. Okay, so this is how you go in this weird chessboard distance. Now you do not say, if we were to measure this distance in Euclidean distance, okay, so in Euclidean distance, if this distance is 1, this distance is 1, this distance is square root of 2, right? This is 1 and this is 1, so this will be root 2. But in this new chessboard distance, this is 1, this is also 1, and this is also 1. It is also called as Chebyshev distance in some books. So now we will see how we can formally define this chessboard distance. So let's take 2 points x1, y1 and x2, y2 in space. And it is defined as the maximum between x1, x2, x1 minus x2 and y1 minus y2. Okay, let us see how this goes. Okay, so let us take this point x1, y1 and this point x2, y2. Okay, so earlier it was the straight line distance. But now we are not going to do that. So you know x1 minus x2 is what? This line, right? And y1 minus y2 is actually this is y1 minus y2 and this is x1 minus x2. So now you don't have to use the Euclidean distance formula to just square this and to get the hypotenuse. You know that hypotenuse formula, right? Pythagoras theorem. But now you will choose the maximum distance between this x1 minus x2. You take this line, and y1 minus y2. You take distance of this line and you choose the maximum distance between this or this to be the distance between this. Do you understand? This is a little bit tricky to understand it. Distance is not the straight line distance now. You will measure what is the maximum between this line and you will assign it to be the chessboard distance between these 2 points. So in this case, your distance will be this much. How much? However it is, right? If it is 3, 4, anything, but this is the distance and not the straight line distance. So let us see what are the different properties satisfied by this distance. Okay. So you can easily see that if you take any 2 points, the maximum between this and anything, it is distance is always positive. You can see. And if you take the same point twice and you are measuring the distance, it will be 0. Otherwise, it is always positive, never negative. Okay, so your distance, the chessboard distance satisfies this positivity property. Let us see symmetry. If you take any 2 points, A, B, you can easily see the distance between this and this is what? Length of this, right? You can visualize now. The length of this is distance between this and you can easily see that uh, this is symmetric. Like if you measure the distance between A to B, it is this, and let's say B to A is this. The length of this is same. So you can say that it satisfies the symmetry property also. Like the distance between A to B is same as distance between B to A now. So it is easy to see. Let us see triangle inequality now. Now this is little bit trickier. Let us say this is your point A, this is your point B, and this is your point, let's say C. Okay. So now you want to check that distance between A and B is less than or equal to distance between A and C plus distance between B and C. This is what you have to check, right? If this satisfies the triangle inequality, this equation should be true. And let us see. Distance between A and B is what now? It will be this line, right? Maximum of this and this is this. Distance between A to C will be somewhere here. And distance between B to C is somewhere here. So check. Distance between A to B is this. Distance between A to C is this. And distance between B to C is this. So you can easily see that the length of this line plus length of this line is greater than or equal to length of this line. So you can see that the chessboard distance also satisfies the triangle inequality property. Okay, so again to summarize, we defined chessboard distance to be maximum of these 2 points, these two lines, these two usual distances, and then we saw that it satisfies three properties: positivity property, symmetry property, and also triangle inequality property. Now let us see this another weird kind of distance which is called as taxicab distance or also called as Manhattan distance. Now we saw that Euclidean distance which is like straight line distance, then we saw some maximum we took. Now let us understand that the tax why it is called as taxicab distance, uh, because we visualize some roads and we can only travel horizontally and vertically. We cannot go like here to here. If we want to travel from here to here, we have to go by this path. So that's why it is called as a taxi cab distance, because we visualize it like kind of the path our car can travel through this lines only. So this is how you visualize the taxi cab distance. So if you want to calculate the distance between this point and this point, now it will not be the straight line distance, neither it will be the maximum of this and this. It will be like this, and this. The length of this path, or you can say length of this path. So you will have to in account all the path you have traveled. So this is what your taxicab distance. Let us see how it is calculated formally. If you take 2 points x1, y1 and x2, y2, the taxicab distance between it is x1 minus x2 plus y1 minus y2. So this is the formula to calculate. Let us see how this formula works. So let us see this. Let us take this point x1, y1 and this point x2, y2. Okay. So you know is this line signifies x1 minus x2 and this is y1 minus y2. Now I said that we can only go vertically and horizontally. So this formula says what? X1 minus x2 plus y1 minus y2. So the distance between this is what? Sum of both these lengths. Do you understand? The sum of both these lengths is the distance between these points. It is not the straight line distance or any what we saw the chessboard kind of thing. It is sum of this both lengths. Okay. So now let us see what are the different properties satisfied by this taxicab distance. So you can easily see the positivity property. If you take any 2 points, this length will be something, right? So it will be positive. So positivity is satisfied by this taxicab distance. Okay. Okay. So, and if you take this point twice, you can easily see that the distance will be 0. Symmetry. If you think about symmetry, if you take A point and B point, let us say distance between A to B is this and B to A is this. But you know this, like this distance and this distance, both are same. So distance between A to B is same as distance between B to A. So you can easily see that it satisfies symmetry property also. Now let us see the triangle inequality property. You will take 3 points A, B and C, and you want to check what distance between A to B. This should be less than or equal to distance between A to C plus distance between B to C. This is what you have to check. So check distance between A to B will be length of this thing, right? Distance between A to B is this. Distance between A to C is, let us say, this. Okay. And distance between C to B, let's say, I should have not drawn it this way, but it's okay. So distance between B to C is this thing. So you can easily see this is the smaller length and this is much bigger length. This plus this, the distance length of this plus this. So this is much bigger path. So you can see that it also satisfies the triangle inequality property. So you saw this another weird kind of distance, taxicab distance, and it is defined as this. We rather take the absolute values of this. So I forgot to mention there, but you may ask like is it can be negative, right? So we take the I will write it here. Okay, okay, I'll write it here. Right? We take absolute value here so that we don't have the negative values to be in the positive and to satisfy the positivity property. Here also we take the absolute values. Okay, so we saw the that it satisfied three properties: positivity, symmetry, and triangle inequality. So that's it for this video. We will see in next video how these three properties satisfying distances, how we can use it to define the metric space. And thank you so much for watching, and make sure you subscribe to my channel and like the video.